It is 2 hours UTC, and it's time for Astronomy Daily Live. Hey, everybody. You can call me Cosmic, and welcome, welcome, welcome. Come on in. Join the ever growing circle of friends as we gather together on our virtual porch with our virtual comfy chairs and our beverage and or consumable of choice. Gather around. Let's talk astronomy for a while. See what's going on. Hope everybody's doing well. Things are okay here. Just sort of normal daily boring life that I have. Intentionally boring. So I have intentional coffee. Intentionally boring coffee. Cheers. And it is the hydrogen hydroxide again tonight, just because it's so calming and so nice. Once in a while, I'll dip into the dihydrogen oxide, or as some people call it, the dihydrogen monoxide. That H2O though is pretty energetic and pretty, you know, got to be taken slowly and gently and maybe a little bit rarely. So cheers to hydrogen hydroxide. Cheers. The most amazing, both both of those chemicals are the most amazing molecules in the universe. Just absolutely mind blowing. So I've got about 10 to the 27th molecules here, more or less. So cheers. So I hope everybody's doing well. Come on in. I'm going to start up my live stream on my smartphone, maybe. And I think it's probably already running over here on my Linux machine. Yes, it is. I want to, hello, Bobby Burgess. Hope everything's well. Jill is singing his heart out tonight. Yeah, you know, I, uh, I think I'm not exactly sure, and maybe you can explain this. I mean, you don't have to, but I think Tim Robinson is posting videos of Gilles singing, and I'm not exactly sure how that works because isn't Tim over in the UK? Um, Gilles is in Montreal, so I'm not exactly sure how that connection is being made. Regardless, Gilles has an amazing voice, and he's very good. Certainly seems to completely um, enjoy himself. So that's bottom line. Bottom line, that's what it's all about. Is if you're having fun, then nothing else matters. So yeah. Uh, Search for Barzo on live stream. Okay, all right. Okay, I I got you. So the karaoke karaoke bar has a live stream. Okay, I think I understand. Gotcha. I don't know anything about live stream. Um, hmm. I'm gonna have to check that out, I guess. Um, I certainly don't know most things. So that is definitely one of the things that I don't know anything about at all. So apparently there's this thing called Livestream. Is it livestream.com, livestream.org, livestream.net? What is it? Inform inform us. You might have to. I don't think you. Yeah, you don't have a wrench yet, Bobby. So you're gonna have to uh, trick the uh, trick uh, the chat into displaying an actual website. link, but I would appreciate that. So yeah, Bar Zoe on live stream. So yeah, let me know what that's all about because okay, well that makes sense because then probably Tim is like recording Gilles and then posting those songs. So that makes logical sense. I hope that's what's going on there. So, all right. Well, hope everybody's doing extremely well. I want to say, I haven't done shout outs in a while. So if you're really into astronomy and want more astronomy than this, I can offer that much, right? When there's just a huge amount. There's the weekly space hangout, and I think that happens Wednesdays at I want to say 0 hours UTC, but and so I guess that would be Thursdays at 0 hours UTC. Uncle Bill, if you're in here, maybe you can help me out with those dates and times. But weekly space hangout for sure. Check them out. Check them out. They are awesome. They're very awesome. Um, Tony Darnell doing deep astronomy is fantastic. Check out deepastronomy.space. Tony is kicking butt and taking names. He's doing really awesome stuff. Great people he gets to talk to, and yeah, I guess just a lucky guy that he has access, um, to those kinds of people. That yeah, always awesome stuff. Oh, so Ustream. Okay. Um, Ustream is what NASA TV uses. Live stream. Yeah. Okay. Well, you guys are gonna have to work that out. See if you can work it out here. Because yeah, I guess I'd be a little bit interested in that. And yeah, I've heard of Ustream. NASA using Ustream. So I don't know if those are the same thing. I sort of doubt it. I sort of doubt it. Appreciate that, Uncle Bill. Um, so yeah, Tony Darnell with Deep Astronomy. Want to give a shout out to oh man, I'm gonna have to pull up my cheat notes here. Give me a second here. Give Uncle Bill a second, and you can give me a second too. Astro, and I think it's oh, I'm doing this a little blind. Live. Uh-oh, now I'm in caps. Live. And I think it's oh man. Let's see. Sorry for the delay. Topics. That's it. Of course, now I remember practically all of them. So weekly space hangout. Weekly space hangout for sure. Dennis R. Hands. He's on Periscope. And he does things. I think he's still doing them Monday mornings at 8 a.m. Eastern Time, United States, and 8 p.m. Eastern Time, United States, on Wednesdays. Um, Tony Darnell is doing Deep Astronomy. And then there's CosmoQuest X with Pamela Gay. There's Skylius on Twitch. You definitely want to check those out. There are a few others too that I need to I need to be a little responsible and get a good decent list here because I want to be able to shout these folks out. You can't. My philosophy is that And I mean, I'm not here to get stuff, get. But um, the only way to to receive is to give. And so I'm all into giving shout outs, right, to all the astronomy folks out there who are, basically trying to do the same thing I'm doing, and that is find our core group who share, a common passion, whatever the passion might be, right? It might be a passion just for, looking at cool pictures. Um, it it might be personalities. Whatever floats your boat is very, very cool, and I want to be able to give a shout out to everyone doing any kind of well, specifically astronomical stuff, but also, just science in general. I just hooked up with Dr. WD-40, right? I guess he's a chemist of some sort, and I love chemistry. I think that chemistry is just absolutely uh, amazing, absolutely amazing. And chemistry is, I mean, to be an astronomer, right? To be a serious, intense astronomer, you have to be a chemist. You have to know chemistry really, really, really well. So those two things, really mix well. So, if I can just sort of, extract some chemistry knowledge from somebody like Dr. WD-40, which is a great name. I'm um, definitely going to do that for sure. But yeah, I need to compile a better list, to give these kinds of shout outs. But what I want to do tonight is I want to acknowledge and wish the Hubble Space Telescope a happy birthday, a happy orbit day. It's been 28 years since the Hubble Space Telescope was placed into orbit around the Earth, and effectively began its service as um, the first, I guess you can say, public space telescope. Uh, so yeah, happy birthday to to the Hubble Space Telescope. And what I thought I would do tonight, at least for a little while, is go to the Hubble Space Telescope archive. I don't know if you knew this or not, but all of the Hubble Space Telescope data, okay, and that is images, spectra, I think that's about it, right? But lots of different kinds of images, multi-wavelength um, imaging, multi-wavelength spectroscopy, lots and lots and lots of data. I think the only stipulation with HST data, and maybe somebody in the chat can correct me on this if I'm wrong, but I think there's a 1 year um, sort of proprietary holding period. So when somebody um, um, uh, gets time, gets observing time on the HST, that data that they get back is sort of solely theirs for, I think it's 1 year. I think it's 1 year, maybe it's 6 months, but I'm thinking that it's a year or so. And that's I think that's fair. I think that's fair because um, it's getting HST time is extremely competitive. I think I heard something like the ratio is like, for every 1,000 proposals, one is chosen. So you know, that might be a little bit of an exaggeration, but probably not too much. So you know, my response to that, of course, is to solve that problem, launch 1,000 HSTs, right? For and I mean, I'm fully in favor of observatories like JWST as well, but probably for less than the cost of one JWST, you could launch at least 10 or 20, maybe 100 Hubble space telescopes, and sort of uh, relieve that uh, pressure a little bit. As it is, you know, it's really hard to get time. Your work that you're doing really has to be worthy of of getting time. Now, I don't think I'm just throwing this out there because I'm, you know, sort of a scoundrel, I guess. But I don't think that there's any kind of bribery or anything going on. I sort of doubt it. I sort of doubt it. You know, these um, um, to allocate telescope time, there's a committee, right? It's not just one person or maybe two people who are allocating time on the HST. There's a large group, and it goes through peer review, and you know, there's a big process. So yeah, I don't think there's any kind of bribery going on like that. um, but so HST time is very valuable. So the fact that that data that is collected by HST is sort of owned by the principal investigator, the PI, for a year, I think that's pretty fair. I think that's pretty fair. Um, yeah, but after a year or so, all of that data, and that's the raw data, that is the calibrated data, and that is the calibration data. All of it is available. So what I think um, is that we should go and look and see, um, look look at some HST data. Hey, Joe Anthony, nice you could join us. You're asking, do I think that the universe has no end? Hmm. I it's really hard to know. I mean, if you want my opinion, I think that the universe is about as big as we want it to be. So I think the the more we look, the more we're going to see. I think that's how that works. Because yeah, I mean, uh, if we can't see anything, then there isn't anything there, at least according to our senses. So is there an end? I think that the end um, only exists in our head. I think that we're going to be able to see anything that we want, right? Sort of the same thing when it gets to the very small, right? The more and more we look for subatomic particles and all that, the more we actually find, the more we actually see. So yeah, you know, to think that there's an end, mm, yeah, I think there's an end only to the extent of what we can um, like um, um, possibly imagine. So yeah, take that as you will. That's I'm sort of sidestepping your um, question, which is sort of a leading question to a certain extent. But let's look for, you know, to celebrate the 28th anniversary of the Hubble Space Telescope. Let us go look at some Hubble Space Telescope data, right? Maybe none of you have actually seen sort of the raw data. You've always uh, maybe have always just seen, the pretty pictures. Um, and, pretty pictures have an incredible amount of value, right? An incredible amount of value. But in terms of scientific value, mm, not much there. Not much there. So I'm going to attempt to share my screen here. And I posted a link over on my Discord server already. So let's go over there and we can start there. And but yeah, Joe Anthony, keep thinking about that because we more than anything else, right? We need um, we need outrageous, crazy ideas, crazy thinking. Um, this live stream um, is about skepticism and open-mindedness. So posing a question like that um, is is going to raise the skeptic flag in my head, but at the same time it also just opens the door, right? It completely opens the door to possibilities. And as a scientist, I want to be both of those at the same time, intensely skeptical but also intensely open-minded, right? So you know uh, um, you know this idea of the universe having no end. I'm wide open to that kind of possibility, but then you have to start thinking about, it's like, well, what do you mean by no end? um, you know, no end in terms of what we can see, what we can sense, or no end in terms of actual space. And when you start talking about what actual space is, it's like, well, what do you mean by that, right? So I mean, it's those kinds of questions for me, really open the doors nice and wide, to thinking and to using our incredible um, imaginations to think of the possibilities, right? And to help us, maybe get our heads into a different, perspective. Um, so yeah, um, it's yeah. So all I can say is keep thinking about these kinds of things because there is value in all of it. So let's go over to the HST archive, and so this is the interface, right? This is what you're going to be presented with, either as a scientist or a member of the public, anything. Um, and this allows you to set a bunch of options, right? Because ultimately, the HST archive is a database, right? So databases are set up to search. So every all the data has been parameterized, right? It's called metadata, and metadata is data that describes the data. So things like the start time, the exposure time, the proposal ID, um, the target name, the right ascension, um, declination, how much of a search radius, if you give certain coordinates, right, you can search for things around those coordinates as well. You can choose different instrumentation on um, Hubble, to look for, right? So what I like to do is I like to just choose them all, right? Just choose all the imagers, all the spectrographs, everything. Um, and I don't know. Does anybody in chat have any suggestions in terms of like a target or like a right ascension declination, anything like that that you'd like to see? I'm going to widen this radius a little bit out to maybe 30 arc minutes. That's like twice the radius of the moon or so. But does anybody have any interesting object? It can be a planet, it can be a Messier object, an NGC object, be the name of a star, um, or any particular coordinates that sort of uh, get you all excited. Anything like that? Anything? I'm sort of waiting because I know that there's a delay in the chat here. So tick tock, tick tock, tick tock. I was looking at Jupiter before, the planet Jupiter. Why don't we look at some Jupiter stuff, and we'll look at science and calibration data. Yeah, okay. The Pinwheel Galaxy, is that M101? Oh no, that's M51. M51. Okay, let's look at M51. I don't know if there needs to be a space there or not. No, the pinwheel is M51, or is that the whirlpool? I don't. I think that's right. Let's just look at this one. Let's just see what we come back with, and we're just gonna let everything else just sort of float here. So we're gonna show all this information. Which instrument, the proposal IDs, blah 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 blah. We'll just leave everything default here, and so let's look for M51 here and see if it comes back. No records found matching query. It's you've got to be. Is it M101? All right. Let's look at M101. Sorry, I got you all excited there for a second. M101. All right, M101. Search. Let's try to resolve it. I didn't mean to do that. Let's resolve that. Oh, it's gathering its information down here. There's probably lots and lots and lots of stuff on that. Yeah, we're it's still loading. There we go. Okay, so number of rows returned 2,081. So there's lots and lots of data from the HST on M101. All right, here we go. So we can sort this by like start time. Okay, let's do that. Okay, so this goes back to 1992, right? 1992, which is what, 26 years ago? So let's just look here. Let's see. This is using the wide field planetary camera, 500-second exposure, using this filter, which looks like 555 nanometers. Let's see what else it says. It's essential wavelength. Here's the proposal ID. Let's look at the proposal. Let's see what they were doing here. So we propose to observe 10 galaxy nuclei from the original GTO proposal 1118 that otherwise will be lost for lack of time. These 10 include 7 of the nearest normal spiral galaxies from type F0 through SC. This is the largest sample of late-time spiral nuclei being done with HST that we know of, and is essential to the collection of a representative catalog of all galaxy types. The remaining 3 galaxies include classic Seaford galaxy, NGC 4151, a prototype, blah, 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 blah. Okay, so they're just looking at galaxy nuclei. And one of them was obviously the nucleus of NGC 5457, which, you know what? Let's make sure that that's actually M101. So I don't know. Let's go over to Sinbad and find out. Come on, Sinbad. Give us some info here. M101. Let's see. NGC 5457. Yay. Okay, so let's just look at this first one. Don't know what to expect here. Now, we're not going to, oh, there it is. Oh, we have access to the FITS data. FITS is, that's an acronym. It stands for Flexible Image Transport System. And it's the file format mainly used in astronomical work. FITS is really, really cool. You can do a search for FITS and read the standard yourself and all that. But what these guys provide is a little, you know, like a JPEG image of the field as well. So there it is. This is actual HST data, right? So what every sensor sees, what every camera sees, is either bright or dark or some shade of gray. And as you can see, or as I hope you can sort of see here, this image has been inverted, right? So the bright stuff is black or dark, and the dark stuff is light. So yeah, for some reason they've decided to do it that way. And it just so happens, well, there's probably what looks like the galaxy in question, M51, right next to a bright star up here. You can sort of see, I think, ooh, you know, let's do something really, really quick. Let's find out when the Hubble servicing one to correct the HST service missions. Servicing missions overview. I want to get a date on when they actually corrected the problems that, okay, yeah. So the first servicing mission was the one that corrected for the flaw in Hubble's primary mirror. So look at that. We're seeing that flaw in the primary mirror. Look how terrible stars look, right? This is what we first saw when we got it up there. It's like, what do we do? What do we do? So this is data prior to HST getting fixed. Very cool. Very cool. All right, let's go back, do another look at something else. So yeah, all of this stuff prior to 1990, prior to what did it say? Like December of 1993. Yeah, yeah. So all this data here uh, was pre-servicing. So let's just look at another one here. This is including calibration data. So you know, who knows what we're actually going to see here. Okay, this looks like a spectrum. Yep, this is a visible light spectrum. Wavelength going from 4,500 angstroms out to what about 6,700 angstroms or so, and we're seeing emission lines here from various chemicals, elements that make up this galaxy. That's pretty cool. Let's see that. Let's see what instrument that was. Does it say? Oh yeah, the FOS. I forget what FOS stands for. There's a 400-second exposure taken on September 26, 1992. Yep, almost 5 minutes long. Yeah, very cool. So this is all FOS. Here's another WIFPIC image here. It says high lat. I don't know what high lat is. Let's take a look. Okay, just another field of view. Yeah, look at the images of the stars here. Ew, yuck, yuck, terrible. Worse than on the ground. Yeah, pretty amazing. Pretty amazing. Okay, so let's go past 19. Let's go into 1994. Okay, and here we go. So here's WIFPIC 2. Okay, which was the replacement of WIFPIC, the Wide Field Planetary Camera 2, which is the fixed one. All right, so let's look at that. Ooh, wow. You can see, look at the image of the stars now. So you're just seeing basically a diffraction pattern, which is exactly what you want to see. But yeah, there we go. So here's just some detail of M101. It's of course not the whole thing. It's just a part. Let's sort of see what these guys were doing. We can look at the proposal summary here and see what they were trying to do. So many fundamental problems in cosmology and astrophysics remain unsettled because the value of the expression of the expansion rate is uncertain to a factor of 2. The refurbished HST will provide the opportunity to break this impasse. We propose a program which, in combination with other GTO and GEO work, should lead to a measurement of H naught to 10% accuracy. So H naught is the Hubble constant. It's a supposedly a measure of the expansion of the universe. So, Joe Anthony, this is sort of tying into your question here. We've theoretically think that we are able to measure how fast the universe is expanding. And so, okay, so our main goal is the observation of Cepheids in 21 fields in 19 nearby galaxy. So a Cepheid is a certain kind of variable star that we have an understanding that there's a relationship between how bright these stars are, and the period of their variability. So if we can measure that period, then um, we know how bright these stars are, and if we know how bright these stars are, intrinsically bright, then theoretically we also know how far away they are. So that's very, very cool. So yeah, that's why this is sort of a zoomed in thing, because they're looking for individual stars in this um, galaxy, and specifically, it sounds like they are looking for um, variable stars. So that's pretty cool. That's pretty cool. In order to do that, of course, you have to take a series of um, images um, at different times. So, hey, Star Strider, say hi to Cosmic Lettuce for me. Cool, very, very cool. Yeah, everybody, and I think that this is just a wave, right? I don't think that I have caused this, but everybody's sort of jumping on to this live stream bandwagon all of a sudden, and maybe it's probably just my perception, but it is a wave that's going on. So, hello back, Pam. Hope everything's well with you there. We are looking at HST data because it's HST's birthday. So we're just looking at some raw HST data. I thought it would be appropriate to do that, to actually see what HST is seeing, sort of unbiased. No, you know, um, pretty pictures are nice, but they don't really have a lot of scientific value. This does, right? I mean, this is amazing, amazing. And they're trying to pick out individual stars here, right? Very cool. Very cool. Let's see. Let's go back. Yep, this one. But this just goes on and on and on, right? On and on and on. We've picked two. Here's a dark. Have you ever seen a dark is a calibration image that is needed in order to properly measure these objects. Have you ever seen a dark frame from the HST? Well, this is going to be an 1800 second long dark frame that was taken on March 23rd, 1994. Let's take a look. It's not very exciting, not very exciting at all. But in order to do science, we need this data. This data is critical, right? Critical data. But it just looks like that. That's it. So you can see these are probably cosmic rays, right? These little streaks. Probably mostly everything that you're seeing in this image is some kind of a cosmic ray, but it's also like electronic noise from the cameras themselves. So that's what raw HST data, calibration data looks like. Just a bunch of dots, but so necessary in order to do good science. So isn't it very, very cool to see that? I don't know what this Earth Calib is. It's a 1.2 second exposure with WIFPIC 2 Earth Calib. Not quite sure what that is. It's not very interesting. Not much there. Not quite sure. Not quite sure. That looks overexposed. I don't know. We can. I don't want to linger on this too much longer. There's, wow, you can spend hours looking at this stuff. Let's go over to the proposal ID 5570 and just sort of see what these guys were up to. Proposal obtains 4 sets of 200 Earth streak flats to construct high quality narrowband flat fields. Oh, okay. Wow. So so they're using the Earth to make their flats. Huh. Earth superflats map the OTA illumination pattern and will be combined with SLTV. Not quite sure what SLTV is, and Cal channel flat fields for the WIFPIC filter set to generate a set of superflats capable of removing both the OTA illumination and pixel-to-pixel response of the camera for science images. Okay. So I guess that's just part of the flat field type of stuff. Let's look at the latest. Let's look at the latest that we have access to here. Well, that's just 1999. Can we, let's go back. We can do I'd like to look at the latest things here that we can see. Let's just, I don't know, let's just do 2018 and see what happens. No records matching query. Let's go 2016. See if that gives us any joy. No, nothing there either. Rah, 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 rah. 2016. Go 0101 or 00000. See if that does anything. No, that's not giving us anything either. Wow. Let's let's go. Oh, got rid of my. Let's go 2014. Nope, nothing there either. It's the start time. So we should be able to do like something like that, huh? Well, let's do this again. Oh, don't resolve. I want to resolve. Oh, maybe that's what it was. I had that not selected to resolve. No. All right. Well, I'm not going to linger too much more on this because this is not very fun and exciting. Let's see. Let's just choose a like a random right ascension and declination. Let's go 18 hours, 22 minutes, 55 seconds, and a declination of so 5 degrees, 5 minutes, 5 seconds, 30 arc minute radius. Ah, wow. Oh, start time. Let's get rid of start time. Oh, there's nothing there. Wow. Let's make this a little bit bigger. Oh, nothing there either. Wow. Well, let's change this to 20. Nah, nothing there either. Well, I'm trying. Ah, there we go. There's something. 105 records. Looks like calibration stuff. Okay, well there's an NGC 6905, and there's a looks like a nova in maybe the constellation of Delphinus, and a variable star in Delphinus. It looks like maybe that's the same thing. All right, let's take a look here. Again, this is the stuff that actually comes down. So let's look at 6905 here. So that was done in 1999, June 29th, using STIS. I think that's a spectrometer as well. So we're probably just going to see a spectrum. Let's take a look. Yeah, okay. The spectra are incredibly amazing, right? There's so much information here, right? How how bright this emission line is, that tells us things. How wide it is tells us things. How much area is under the curve, that tells us things. And I would I would dare say pretty much every wiggle in here is has some kind of significance, right? And again, these are showing elemental constituents. I'm not exactly sure which ones these represent, but we're looking at the emissions of atoms inside of this galaxy, right? And it looks like this is ultraviolet wavelengths, right? Because this is going from what maybe about 1700 angstroms up to about 30 3100 angstroms or so. So that's on the blue side of the visible wavelength. So that's ultraviolet. That's an ultraviolet spectrum of this galaxy. Not even quite sure. Let's go back over and see what 6905 is really quick. Let's see, 6905. Probably is a galaxy. It's my guess. 905. Oh, it's a planetary nebula. Oh, cool. Wow. Nifty. So let's look at the proposal. Just see what these folks were doing. That was an 800-second exposure. Let's look at the proposal here. UV and optical spectra of hot pre-white dwarfs and white dwarfs, often in planetary nebulae, show emission from ions characterizing temperatures far above that of the photosphere. This includes emission from oxygen 7 and oxygen 8, as well as other species. The unusually high ionization emission features suggest a chromospheric-like region around these objects. We will use the spectra and imaging capabilities of STIS to observe these objects with the goals of A, determining what high ionization features are present, and B, map the extended nebular emission, and C, derive ionization structure at larger distances. Well, cool. So they're looking at, I guess, the emissions from the white dwarf stars inside of a planetary nebula here. Very cool. So this is the spectrum of a white dwarf star. Cool. That's awesome. Looks like they've got little bit of data there. Yeah. Let's see, is this the same? You can go over and see if it's the same proposal. Okay, so these ones are the same proposal, but this one's a different one. So let's see what these guys were up to here. This is with pick. So okay, with pick. So this is, yeah, kind of hard to see, but this is with pick, which means it's the uncorrected. Ooh, nasty looking stars there. Yeah, pretty nasty looking stars. What date was that? Okay, that was right before, right, 1993. 1993. Let's see what else we got here. So Nova Delphinus is in the same area. Oh yeah, see all these observations of the same proposals. Let's look and see what these guys were looking at. Nova outburst results when sufficient mass accretes from a companion star, blah, 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 blah. Yeah, so they're looking at what looks like a nova event and just getting as much information and data as they possibly can. So let's see, they were looking, they took spectra, right, STIS, and with pick 3. So yeah, this is pretty new, right? This is pretty new stuff here. So let's look at the pictures first, I guess, if there is any. Oh, nope, there isn't any. Might be proprietary still, hard to tell. Let's see, let's go back. Let's see if there's at least a spectrum. Nope, no spectrum either. Not quite yet. So yeah, that might be under proprietary use still. Unfortunate for us. Fortunate for the folks observing this. Here's some more spectra. Looks like this thing pops pretty regularly. Okay, yeah, so here's a spectrum. Another ultraviolet spectrum. Kind of noisy. Maybe, yeah, pretty noisy. Very cool, though. Let's see what these guys were after. Major obstacle in understanding the classic nova phenomena is the lack of systematic observations, primarily spectroscopic, through the various stages of the ejecta and white dwarf evolution. Okay. Our objective is to use HST, STIS spectra along with coordinated space and ground-based observations to fully characterize 3 bright recent galactic classical novae within a panchromatic framework. Okay, cool. And one of those is V3339, which is the one we're looking at here. This is just, I just randomly chose this. No reason whatsoever at all. Looks like these were done back in 2015. Let's look at a couple other of these. See if there's any differences. Oh, that's kind of weird looking. Kind of weird looking spectrum there. Let's look at this one. Yeah, I'm not quite sure. Not quite sure what we're seeing here. If we're actually seeing emission with some broader emission lines here. I'm not quite sure. Once the flux goes negative, my flags go off in my head saying this is probably not calibrated data. So yeah, hard to know exactly what we're seeing here. If this is raw data, just like I've said, before, if this is raw, uncalibrated data, we really don't know what we're seeing here, right? Looks like a mess. Just looks like that snowstorm, right? Let's see. We'll take a look at a couple of these other ones. Oh, nothing there. Oh, looks like I'm accumulating windows here. Let's see. I think this was a different one. This is more spectra. Let's see if there's some pictures. It's like a lot of these are. Let's look at a WIFPIC 3 dark. Haven't looked at that yet. I don't think. Have we? That's kind of interesting. Not quite sure what we're seeing here. That was supposed to be a dark, but yeah, I'm not quite sure. Blank filter mode, multi-accum. So yeah, I'm not quite sure why we're seeing. I'm not sure. Maybe this is, this might be like a bad pixel mask or something. Yeah, hard to tell. Hard to tell exactly what we're seeing there. But all of this is so important to extract that useful scientific data. So there's some more apparently darks. Half a second exposure time there. All very exciting looking at blank data. See, that's why public images, you'll never see this, right? But if you tune in to Astronomy Daily Live, you're going to see all the shit, all of it, because it's really, really important. I mean, this looks like nothing, but this kind of calibration data is necessary in order to allow us to understand what we're seeing in the actual data. Cannot emphasize that enough. Really important stuff. It looks boring. And yeah, from a certain perspective, it is. But it's so important to be able to have this kind of information available. So let's see. Don't really see anything else. Let's do one more. Let's do one more. I'm going to do one that I guess I want to do here. Let's do Jupiter, the planet Jupiter. So we don't have to resolve anything here. Let's go Jupiter. (886) observations here. Start time, stop time, sort by. Did I do it? I don't know. Did I? I don't think I did. There we go. Here we go. So these started back in 1992. I think I clicked on that many times. So let's look and see what the latest WIFPIC 3 image, 30-second exposure, taken in April of this year. So let's see if this is available. I don't know. Nope. Preview for this observation is not available. Not even the data is available. So let's look at one of these. No, I'm sort of going by this yellow thing. Maybe that's the proprietary period is over. Let's find out. No, that's not available either. Wah. Well, let's go back even further. Lots of observations of Jupiter being done by HST. Oh, that's not available either. Wah. Next. Let's look at this one. 2012. That's got to be available. There we go. Okay. So I don't remember what this is. Let's see. So this is with pick 3, 763 nanometers, probably. So that's looking in the very, very red, right? That is looking, pretty much in the infrared. 0.48 second exposure time, and there it is. There's Jupiter. Again, this is a reverse image, and it's also a JPEG image, right? So it's been shrunk down. Um, you know, this isn't the actual raw data. If you want the actual raw data, you have to load up the FITS image, which I don't think. Let's see what this does. Yeah, see, it's going to try to do that. So there we go. There's an HST image of Jupiter. Let's see. They probably have multi-wavelength things here. So let's see. We just looked at this one. We can look at another one in the ultraviolet. Right. Here's another one in the ultraviolet. There we go. Now, one thing that I didn't look at. Yeah. Okay. See, so these were taken pretty much at the same time, right? This was taken on September 20th, 2012. This at 6:06 UTC. This one was taken at 6:09. So pretty much, simultaneously, they're taking an image in the near infrared and also, sort of the near ultraviolet. So there's the ultraviolet image, pretty much of exactly the same thing. Ooh, look at that. Ooh, I wonder what that is. That's kind of weird looking. Don't know if that's part of Jupiter itself or if that's maybe an artifact of some sort. I don't know. Did we see that in the infrared image? I don't remember. Oh yeah, I guess we sort of did. Yeah, it's this structure here. Yeah, very, very cool. Very cool. All right. Well, look, I think that's enough. I mean, there is so much here, right? There's so much here. You can look anywhere in the sky, right, and find this kind of stuff. The cool thing again is that, if you're so inclined, you can this data is freely available. You can go and grab it. You can do science with it. You can make, pretty pictures. You can do whatever you want with it. This is our data. This is our data. So it's very, very cool. It's very, very fun. I thought I would do that for the orbit day, the birthday of the Hubble Space Telescope. 28 years. It's been up there 28 years, and it's still going. It's still going. I would like to see hundreds of HSTs up there. I think that is the way to go. I'd like to see, lots of JWSTs there too. But, lots of HSTs. Yeah, I think that would be very, very cool. All right. Well, I think my nose is itching, and yeah, I'm getting the call from the mothership. I think it is time to exit these waters for now. Hope you like that. It's I think what I'm trying to showcase and show off a little bit is maybe a little bit different than what you're used to seeing. Um, don't know if it's interesting or not. It is intensely interesting to me. So yeah, hope you like that. We can do this again. There's so much data. It's this unbelievable amount of data. Um, and it's great, just to look at it and try to think about what we're seeing and what the relationships are and all of that. It's very, very cool stuff. The universe is an amazing place, and we are scratching the surface, right? We are just barely scratching the surface in terms of all this stuff, but it is so cool, and I'm in awe, right? I'm in absolute awe. So, all right, I am going to get out of here. Take care. Peace. Cheers. Have a great evening, a great day, and I will see you on the spin tomorrow, a little less than 23 hours from now. All right, take care, everybody. I will see you tomorrow. Bye.